Representing Alabama A&M University, our research project this summer was simulation of linear circuits and analog circuits for smart city applications. Our undergraduate students, Nick Crenshaw, Peyton McDonald, Eric Skeet, and myself, RET participant Shauna Hampton, as well as our faculty advisor, Dr. Budock, and our graduate mentor, Lauren Kroom. In the future, smart cities will use hundreds of thousands of small, low-power, interconnected smart devices to perform a huge amount of tasks designed to improve the lives of cities' residents. Many of these smart devices will have complicated circuits as key hardware.
So the objectives for our experiment were to learn and operate effectively the NI Multisim software in order to simulate linear and analog circuits for smart city applications. The linear and analog circuits, just to name a few, that we worked with this summer included mesh and node analysis, superposition theorem, operational amplifiers, diode and its applications, diode analysis, BJT or bipolar junction transistors, and as well as Junction Gate Field Effective Transistor, also known as FET. The methodology for our group was to learn the Multisim software, learn the basics of linear and analog circuits, and applying knowledge towards real-world applications. In week 1, our group learned to operate the NI Multisim software, as well as how to calculate the individual resistance of a resistor. We were able to construct our own sample connections via the software, as well as experiment with some of these sample projects within the software itself. The circuit analysis consisted of series and parallel resistor combinations, which included open and short circuits. A resistor is a basic electrical circuit component. The property of a resistor is described by Ohm's law, which states that while the temperature remains constant, the voltage across a resistor is proportional to the current flowing in it. And here is an example of the parallel resistors in figure 1 and series resistors in figure 2. Throughout week 2, our group worked with mesh and nodal analysis, and here is a picture of that. We were able to measure the voltage and current values. Both of these methods are based on the application of KCL, KVL, and Ohm's law. Mesh analysis involves in relating the actual currents and voltages in the elements to what they are called mesh or loop currents. These currents are sometimes virtual and cannot be measured in certain circuits. Node analysis involves in relating the actual currents and voltages in elements to what they are called node voltages.
So in week 3, we went over Thevinin and Norton equivalent circuits, which is a theorem that at least any linear circuit can be reconstructed in this form with one voltage source and 2 resistors to make it simpler. Here in this experiment, we would use, in this picture is the end of a lab experiment that we did where we had to use Multisim to create a Thevinin equivalent circuit. We used a ohm meter to find RTH, the total equivalent resistance of the circuit. And then we would also find the open circuit voltage and the load resistance. In week 4, we went over the properties and applications of op-amp and diode circuits. On the left, what you see is a diode circuit, and it's being analyzed with an oscilloscope. And on the right, you see a op-amp circuit. Some of the applications we went over for op-amp and diode circuits were for an op-amp, an audio mixer where you can control the input sources and balance the output. And then for a diode, we went over a AC to DC converter, which is used in charging most electronics. In week 5, we went over RC, RLC, and any other combination like that circuits. Here in the top image, you can see us analyzing an RC circuit with an oscilloscope to see how the capacitance stabilizes over time. You can also notice that the source we use is a square wave source, which is the first time we've encountered this. In the bottom image, this is an AC RLC circuit. In week 6, we went over the BJT Common Emitter Amplifier. Here in the center, this circle in the center of the screen, that is the actual BJT. And then we measured the voltages throughout this circuit.
In week 7, we went over JFETs, which are Junction Gate Field Effect Transistors, and we went over BJT Common Collector Amplifiers. Bottom left is a picture of a JFET circuit that we went over, and top right is a picture of the BJT Common Collector Amplifier. So here's our first application that we went over. This is an AC to DC converter that is used in many chargers for cell phones and computers and other electronics that run on DC power. As you can see, it takes the AC input from the left and converts it to DC input shown on the multimeter screen on the right. Here is the second application we went over during the summer. We looked at an audio mixer, which takes these 3 inputs on the left, the singer, guitar, and bass, and converts them into a single output on the right. This is a picture of all 3 inputs being converted into an output altogether when the R2, R3, and R4 on the left were at 80%.
An example of an audio mixer that we connected in Multisim during week 4. An audio mixer can be used to make soundtracks for movies and TV shows, and or to adjust audio inputs such as voiceovers, sound instruments, and things of that nature. Some of the components used in this example are 3 AC sources that we named singer, guitar, and bass, 3 potentiometers, 2 DC sources that supply the op amp with upper and lower bounds, as well as 4 resistors.
Okay, so to get this audio mixer to work, we have to connect all our sources or components together, sorry. We start off by connecting the input sources into our potentiometers. The potentiometers are what allow us to physically change the input of each source into the op amp. Potentiometers are then connected to these resistors, which are in turn connected to each other and to the op amp in pin 2 and to resistor 7. Pin 3 is connected to a ground, and then we have to connect our upper and lower bounds for the op amp to work. Upper bound being 15 volts, the lower bound being negative 15 volts. The output, which is pin 6, is then connected to the oscilloscope along with resistor 7. And now you are ready to analyze the circuits.
So we decided to do 4 different simulations on this experiment. The first one being when all 3 sources have an equivalent input into the system, and that gives us this waveform. If I then minimize the singer's role in the input, you can see that the amplitude decreases and the frequency is about the same. And then if I take the bass and I maximize its role, you can see we get this waveform where the frequency decreases and the amplitude increases. And then if I do the same for the guitar, we get this waveform where the frequency increases and the amplitude increases as well.
So in conclusion, for the use of smart city applications, this is an example circuit that can be used to amplify sound of security footage to enhance public safety.
So our results for our summer research was that we learned to analyze resistor networks, and we used this knowledge to combine resistors and inductors and capacitors into several different circuit um, designs and analyze frequency data from those. We then learned how to use transistors in several different circuits, including amplifier circuits and switch circuits. And we also looked at several real-world applications, such as the AC to DC converter and music mixer.
So in consideration of how we can use the summer's research in my classroom or in classrooms at my school, we can first consider the designing of circuits. So there's a high application of current content standards in physics and engineering courses to the circuit design that we did this summer. We can also apply it to my AP Environmental Science course by looking at how circuits work inside of our energy unit. The second way is looking at our math practice. So a lot of the equations and mathematical formulas that we use this summer would be great additions to our algebra and our geometry courses, as well as manipulating variables in dimensional analysis in all of our courses, but especially in mine where we see it most often. And then the most pivotal point is continuing collaboration with Alabama A&M through online Zoom meetings, in-person lab days, and ways that we can actually continue to apply this research to this real-world practice in both our engineering and physics courses and as well as in my own classes. And there could also be an application to our biomedical courses if we consider the way that circuits are designed for medical technology.
Future work that can be done by industry and academia include the improvement of smart and electric car battery life and efficiency. Companies such as Tesla, who is a major electric car manufacturer, is currently doing this because they want to be able to produce their own car batteries and increase the driving range of their electric cars. Companies can also improve the efficiency of homes by creating smart homes, which would decrease the power intake of electronics while improving or keeping their original performance. Companies like NVIDIA are currently working on this with their new GPUs that cut in half the power intake and increase the performance by around 20 to 30%. Then finally, industry can work on the creation of more efficient, non-pollutive fuel sources, including solar, hydroelectric, and nuclear, so that clean fuel is not such a small proportion of the fuel sources in the United States.
So future work that we can do as students would be getting hands-on with the experiments that we performed in Multisim. That includes designing the circuits and putting them on a breadboard, and then running the circuits through similar tests that we did in Multisim and seeing how close the values we get. Then we can work in a physical lab, studying specifically the ways that real-world circuits differ from the perfect examples in Multisim, and seeing how certain things might not be as consistent as they seem in a computer. And then we can get into more research programs that study this area in electrical engineering.
And here are our resources.